Hey, hi everyone. I think we're getting some feedback. Okay, right. Hi everyone, and welcome to our Open-Endedness panel. So yeah, today our speakers will be Danja Hafner, is a PhD student in artificial intelligence at the University of Toronto with Jimmy Ba and Geoffrey Hinton, and he is also a researcher at the Brain team at Google Research and the Vector Institute. Denjar's research focuses on building intelligent machines based on the computational principles of the brain and evaluating them in complex simulations. We also have Kenneth Stanley, which leads the team at OpenAI on the challenge of open-endedness. He was previously Charles Millikan Professor of Computer Science at the University of Central Florida. His main research contributions are in neuroevolution, generative and developmental systems, coevolution, machine learning for video games, interactive evolution, quality diversity, and open-endedness. Max Schadenberg, who's a research scientist at Open-Ended Learning Team and Open-Ended Learning Team lead at DeepMind, and he co-founded Visual Factory, which was acquired by Google in 2014. And Chim, who's a research scientist at FAIR, Facebook AI Research, London, and associate professor at the Center for Artificial Intelligence in the Department of Computer Science at University College London, and a scholar of the European Laboratory for Learning and Intelligent Systems, ALICE. Okay, so hi everyone, and let's begin. So I guess the first question would be, can you try to define like open-endedness in one sentence, something like very short, and explain why do you think it's important to study it? Let's begin with Ken, because he has a book on that, and then we go alphabetically.
Okay, one sentence. This is a challenge. I'd say it is the continual generation of artifacts that are interesting to us without bound forever.
Nice.
I mean,
And
how
why?
can you top that? You know,
That's a good question.
And why do you think that's important?
Why do I think that? Well, I think that's important because that is, I mean, like Max said, I mean, how can you top that? That's pretty much the most powerful process you can imagine. Of course, the word interesting is instrumental there. Like it's basically saying, when I say interesting, I'm saying like it's something that actually we would care about. So if there's actually an algorithmic process that continually produces things that we care about as humans, I mean, the value is hard to estimate. But I guess the other side of it, which I would throw in here as probably discuss, is that there's a hypothesis that something like that, a process like that, is necessary to get to AI or AGI, as we're calling it today, and that we aren't going to be able to get there through like a typical types of objective-driven convergent processes. So we may need open-endedness to get to AI, but open-endedness in its own right, I think, is extremely valuable and interesting and worth achieving.
Nice, cool. And you, Danger?
I think there's probably two aspects to open-endedness. One is not being bound to a specific task, because that would be pretty limiting. Of course, the system has to come up with its own ideas. Or at least it has to have a lot of different behaviors and skills and things that it learns in the world. Yeah, so not being bounded to one task, and then I guess I don't know, I forgot the second point, but I think I don't know if I guess there's a lot of different definitions and things you can say, but ideally we want a system that can learn by itself, because in practice we won't be able to provide very detailed feedback if we want the system to learn something like a very challenging task.
Okay, and yeah, I think you already kind of said why is it important, right? On this matter of we can't like always give you the task.
Yeah, and on the other hand, maybe here's the second point I was thinking of. Of course, the world keeps changing, and the system will always be thrown into new, like at least in the real world, in like a scenario that people are learning in. There will always be new situations that you're thrown in, and so you have to keep continuously adapting to what's happening. You will never know enough about the world to generalize perfectly to your new situations. So in machine learning, we like to amortize things a lot and just hope that we generalize to whatever comes at us. But in a complex real environment, adaptation becomes really important because you won't be able to generalize to everything.
Nice. Yeah. Thanks. And Max?
Yeah, I mean, I think that's kind of like the key point, and especially like why open-ended learning and open-endedness is important, especially now, is we can see the success of deep learning and machine learning on fixed objectives, right? But what happens is, as Dan says, when you have like many different tasks, or even if you think about just one big environment domain, and think about AGI, as that domain gets closer and closer to the real world, where the scope of possible things that you can do within this space by an agent is so large that you could never fully understand this space, and also the many different tasks you might do within this space might conflict with each other. So there is no way to encode this into a single scalar objective. And in that sense, with that view in mind of wanting agents which can not only exist in this space but thrive in this space and start to discover and have agency within ever more complex environment spaces, we need to think about learning processes, open-ended learning processes, which, as Ken was saying, automatically discover the sort of interestingness in this space, the continued depth in this space, in ways that we couldn't like humanly code or bias.
Yeah, that's a pretty great answer. And Tim?
Well, I think there were lots of really good explanations and ideas already mentioned, so I'm not trying to not repeat too much. But I think I would like to contrast that just with, I guess, how we've been doing research in quite kind of closed environments, right, in the last decades, right? I mean, it's eventually, right, we want, as was mentioned already, we want agents or AI that can be used for real world problems. So the goal is towards learning agents that can do something sensible in the real world. So with that in mind, right, we have to move further and further towards environments that are much more complex, much richer, that remove many of the simplifying assumptions that even current state-of-the-art agents are still exploiting. Things like having a deterministic environment simulator, being exposed to only kind of a limited set of variations that an agent has to generalize towards. To all of these things, I think we have to step by step remove, and that's why I think it's so exciting to see so much recent interest in research in open-ended environments and agents that can by themselves explore in these environments, can set themselves objectives, can even learn to generate instances of environment to then come up with a curriculum over time to get stronger generalization behavior to held out test sets. I think that's it's really exciting time. But I think, it's really important, I think, to just contrast that with what we've been doing, or some of us at least. I think Ken has been in this business for longer, but some of us have been focusing too much maybe on too simple, narrow environments.
Great. And now for the next question. So this time we will do like reverse alphabetical. So it's Tim, Max, Ken, and then Shar. So neural networks, do you think they are fundamental for reaching open-endedness, or it's more something like a hardware lottery? And if we had some kind of tree processing unity, we would be talking about like random forest for open-endedness. Yeah.
I mean, I think there's we like using neural networks as deep function approximators, right, to learn from data to at least interpolate between, I guess, data points that are given to the neural network. Whether or not your open-ended agent uses much more than that, I think it's not really, I think, the point, right? The point is, as Ken said, like we should have some kind of mechanism that can accumulate more and more interesting artifacts and show more and more interesting behaviors. Neural networks, I'm pretty sure, will play some role in terms of learning to represent inputs. But who knows? Like maybe it's going to be a neural symbolic system that does the best in the future. I don't think we need to like put all our eggs in one basket. I think the way we learn to represent, for example, inputs can be potentially thought of differently from how we kick off a process that over time accumulates this kind of complexity and richness.
I think maybe to carry on from that, there's also the environment space itself. And for open-endedness to even be interesting or needed, we need to get some sort of like complexity out of this space and some complexity of interaction between in the dimensions of the environment and the agents acting, whatever form these agents are acting in this space. And where I think neural networks can play a really big part is in providing these like really complex dynamics and interactions. We want dimensions of the environment. Think of weights of neural network that interact with each other in sort of almost chaotic, complex ways. So there's a huge scope of emergent dynamics that could come out of like the evolution of these states of networks, which can also play off the dynamics of, an external environment, such as a Unity simulation as well. So I see neural networks not just as a way of like state representation and like functionally, making these agents move about, but actually like to produce complex emergent dynamics within much simpler like linear simulations or physics simulations.
So it's me, I think. It's all right. Okay. So I think that it's, at least theoretically, it's pretty clear you don't have to have neural networks to have an open-ended process, because natural evolution is an open-ended process, and it's one of the inspirations, I think, for the area. And natural evolution is not neural networks don't play an instrumental role in that process. If you go back like to the first single cells on Earth, and then you go for hundreds of millions of years, there's no neural networks, but there's still an open-ended process happening. And that sometimes, I think, maybe in the recent years in machine learning where open-endedness does come up, that gets missed a bit. Like we don't talk so much about those early years of open-endedness. And that's probably because neural networks do come up and become really important once intelligence starts coming into play. If you think about open-endedness sort of historically, like what is the inspiration for studying open-endedness? Like it's a huge continuum that goes from like the first single cells in natural evolution all the way up through like the discovery of human beings, and then civilization, which is another like gigantic continuum, which is its own open-ended process. But so you could look at it as like these two things where there's like natural evolution, then there's civilization, or you could look at it as one giant continuum where it's all just a single type of process where one thing leads into another. But it's sort of in the civilization phase where neural networks really come into play strongly. And I think also in the study of AI, because then we don't have a lot of other tools in the toolbox right now that are great alternatives for imagining increasingly complex intelligences sort of like somehow interactively arising without something like a neural network. But maybe we would think of something, but right now I think it makes a lot of sense to focus on neural networks there. But I think overall as a field, for open-endedness as a field, I think it's useful to try to understand the entire continuum from evolution through civilization, because there's something like, if you think that open-endedness depends on intelligence, then you're missing something. It's something fundamental, because it's really incredible that a process like this could run without an intelligence behind it. And we need to grapple with that as well and understand what that means, because that will help us even in the civilization phase to understand why these kinds of things happen.
Cool. A lot of things have been said. I feel like that was pretty exhaustive already. I guess in terms of intelligent open-endedness, you definitely need to adapt. So you can't just have a couple of hard-coded rules. Like those rules, you either have to look at a lot of the past experiences that you already got as an agent for making your decision, sort of like a non-parametric model, or you can summarize that knowledge into parameters, and then you get a parametric model for making your decisions. And neural networks are the best for that, for those parametric models that we have right now. I do think that maybe we'll move towards hybrid models that have some parametric, some non-parametric components in them, because that could help with generalization. Could also help with avoiding unwanted generalization. Sometimes neural nets are kind of confident of like, the world is, I know the rules of the world here, I kind of can predict what's happening over there, but really you have never been there and there might be something surprising. So if we're thinking about like exploration methods in RL, there are a couple of interesting, more recent ones that integrate some of these non-parametric aspects. But I mean, we might build something much better than artificial neural networks at some point, so I wouldn't be too set on it. It's just the most practical to use right now.
I've got maybe like a follow-up question on Ken's point, maybe for Ken. If we have this open-ended learning process, forget neural networks, and it just keeps creating complexity and discovering more and more interesting things. If we're simulating this on a sort of fixed memory computer, do we get to a point where we have a compression issue, or like we have a data issue, and we need some form of like compression of like dynamics so that we can continue to be open-ended with a sort of fixed compute and memory budget? And is that maybe where neural networks or sort of intelligence comes into play and keeps allowing that progression of open-endedness?
That's a unique question. I don't think I've thought of it that way before. So do we end up with a compression issue because there's this effectively finite space, and we certainly end up with an issue, that's for sure. And I guess we have to grapple with the finitude, I guess, of the computer, which is a little different from like just Earth, where it is also finite, but it's so gigantic that it's like practically infinite for a long period of time. And that does cause a lot of trade-offs and compromises. Like if you're really trying to do an open-ended system, and I think that like in the field of artificial life, where open-endedness had a lot of attention preceding machine learning, that was, I think, historically a challenge dealing with finite memory. But does that actually lead to a like sort of explain or entail neural networks? That part I didn't completely see that, or how that connects. I'm interested in that though. How do you think about that? Why does a neural network follow and sort of address that issue necessarily?
Due to the generalization capabilities of the compression capabilities of neural networks, essentially, like instead of storing raw behaviors somehow, you can compress this and with the same memory and compute, or like same memory footprint.
I see. So because I guess whatever these agents are, I mean, pre-neural network, they don't have that kind of compression, presumably. So I think, it seems like that helps in some way, but it's very complicated how that comes into play to facilitating the entire open-ended process, or like what would happen. Right? Yeah. If you want to do a very A-lifey pre-neural network type of simulator, like very low level kind of game of life type of a thing, like is there? I guess it's just somehow like if it can't flip to neural networks, it's limited. Maybe that's true theoretically somehow, or something like a neural network gets you farther. But ultimately, like we're also dealing with, with memory trade-offs. You have to be really, really careful, just even with neural networks, about what you're going to get rid of and what you're going to preserve, and where you're going to go and where you're going to prune. And I think it's more acute because of this for us in a computer than like just the planet Earth or something like that. So like, there's a lot of problems I think that come up beyond just this issue, because things are finite in a severe way, and we're trying to do things that are sort of analogous to the natural world, which is much different in sort of that finite sense. And so that is a tough algorithmic problem for this area.
Right. I mean, it's almost like the opposite, right? I mean, in the real world, like you with evolution, you get these organisms that then basically, if you take them as a total set, right, increase the computation over time, right? You have more kind of networks that can process information, whereas we are definitely limited by computational resources. I mean, I also have a question for Ken. I mean, maybe related to that topic, right? In open-endedness, we often have this kind of, I guess, idea of a process that creates more and more complex and interesting artifacts, as you said, right? And you have this really interesting example in your book, Why Greatness Cannot Be Planned, where you imagine this kind of gentle Earth where, we have this kind of open-ended process, but there's not much kind of harsh circumstances on Earth that prune away organisms. And I find, I mean, I would just love to pick your brain in terms of, to me, that just creates a huge blob of gray, uninteresting stuff, right? To me, it seems like the biggest challenge in open-endedness is actually, as you said, like this pruning, right? How do we make sure we still somewhat stay in a very creative process while making sure the things that we keep around, given our finite constraints, are not just uninteresting blurb?
Yeah. So this gentle Earth kind of metaphor was about a sort of thought experiment in the book, which was saying, look, this is something really interesting here. If you consider the fact that, like, if you had the same mutation distribution as Earth and you just started out from the first cell, whatever that was, the first living thing, you'd get basically everything that we have. And so, like, it's sort of saying, like, maybe we should think a little bit more about, like, the explanatory apparatus of natural evolution beyond just like an optimization process, which is sort of saying, like, if the fittest survive, we get all this really great stuff, and that's the explanation for why that stuff is here. It's rather like, because this thought experiment, I think, sort of how you said it, sort of suggests more that really what this process is more about is what is not here and what is here. Sort of saying, what won't we actually pursue? And then what should we keep from all that set of possibilities that would come out of that distribution? And so that, I think that's just interesting to think about. And it shows that we are making very important choices when we choose what to throw away. But at the same time, like, I think it would be probably, in the best system, would basically not be throwing anything away from an open-ended sense, even though that's completely impractical. But like in some hypothetical, theoretical situation, I'd like to see everything. Like, there's no pathway that I want to throw away. I want to see all the pathways and where they go. You're concerned with, like, a lot of inert blobs filling up the planet. Of course, this is just a thought experiment, so obviously everybody would die if a situation like that was occurring. But in the thought experiment, there's plenty of space. There's no problem. Everybody's going to live. And so, it's just a matter of picking out the stuff that's interesting. Now, that's not a trivial problem, but the problem, though, isn't that there aren't things that are interesting. Like, we're still there, presumably. You and I are still here. We're just surrounded by lots of inert blobs. And so we're some tiny percentage of all of the, like, living mass, like in this hypothetical world, but we're still here. So the interesting stuff still gets created. So you don't need the explanatory apparatus of natural selection to explain why we're here, which is really weird and bizarre to consider, because it shows that part of why we're here is because of the a priori structure of the universe, which is really strange. It's basically the structure of the search space is partly responsible. It's not just selection and optimization. And so I think it raises important questions, but in a practical level, it emphasizes how picking what not to pursue is really, really what's important here, because there's so many paths we could go down in a divergent process, and we can't afford to because of finite memory.
Oh, yeah. So, okay, let's go for this last, like, mind question, and then we go through the audience questions. So, yeah, each of you have, like, specificities to your method. So Danjar uses model-based RL, Ken uses evolution and genetic algorithms in general. Tim has autocurricula. Max also deals somewhat with autocurricula and with the population-based stuff. So my question is, why? Like, why do you think your specificities are interesting or important, and, like, how did you come to them? And let's start with Max because he has, like, only 3 minutes.
I don't think the specifics are that important, to be perfectly honest. I think what's important is somehow setting up this. I don't think of it as like a learning agent and an environment. Instead, it's like one big dynamical system where there happens to be a neural network which is learning in the loop of taking actions in an environment. But there must also be feedback from the agent's behavior to influence the environment distribution, or something about the environment's like states that are given as well. And for this system, this dynamical system, this joint dynamical system, to be set up so that it could potentially create just emergent complexity forever. One of the tools that we used in our project was to have other agents parameterized by neural networks as a way, to build emergent complexity in the system. But it's not the only way. And to do that, we use population-based training and generational training and all this sort of stuff. But I don't think those specifics matter on a wider level. I think it's more like, how can we actually practically today build these like dynamical systems that have really like rich and complex emergent properties as we run them.
And
Yeah.
I just wanted to congratulate Max on the work on Excellent, because that is very thought-provoking. Just want to say that before you stepped out, because I know you have to go. I don't know actually if it's my turn.
You can go ahead.
Okay. So I was paired with evolution, and it's true, I spent a lot of time using evolution in my career. And so why? Well, I guess the reason is because it's such an obvious example of an open-ended process, like evolution on Earth. And so I felt that you could draw a lot of insight from trying to understand it. And one of the things that kind of captivated me about it is that it's not understood, apparently, because like from an algorithmic perspective, if it really was understood, I mean, forget about genetic algorithms and stuff. Like, we know we have algorithms like that, but just think about natural evolution. If that's really understood, then we could just redo that. We could recapitulate natural evolution in computation. And we are far from being able to do that even now, even though we've learned some things over the years. And that means that it's much deeper, actually. The explanation is much deeper for what happened over the course of evolutionary history than what you read in your biology textbook, because otherwise that would be a reference for my computer science experiments. And it's not. And so there are deep insights to be had. And really, though, like Max said, the issue isn't so much that like that particular toolbox of evolution and genetic algorithms is like the one for doing open-endedness. Like, I totally don't believe that at all. I just think that like we want to look at things that are playgrounds which will elicit like these deeper principles, so that we can start to grapple with them and understand them. For a long time, I felt like evolutionary algorithms, not in the conventional sense of like a genetic algorithm, but more exotically, like things that are trying to get deeper into what happened over the course of nature, like that those were a convenient playground for like sort of teasing out some of these principles. And I believe they did prove to be so, because like things like the emergence or like some discovery of things like novelty search, which is highly relevant to open-endedness, and some other things come from playing in that playground. I don't think it's impossible that it could have been a different playground. Like the whole framework of machine learning and reinforcement learning and deep learning, like it could have emerged from something like that, although back when I started, those things weren't really fully the way they are right now. But evolution is very convenient as a playground. It actually lets you sidestep a lot of issues that took like decades within like gradient descent and stuff to get a handle on, that were very easy to set up like through fitness functions and stuff like that, and just get directly to the heart of the matter of open-endedness much faster. Now today, I think things have shifted a bit because of the fact that these methods now are so sophisticated. And so like it's becoming less clear that you need to use evolution like to address some of these deeper questions. But everything should be on the table, sort of like what Max said. I think we shouldn't be partisan about our methods, what we should be thinking about, just if we're working on open-endedness, is what is going to help us get to the next deeper, not necessarily solution, but question is really what I think is important. I like methods that lead to more questions, not answers, because like the real thing is like there are things we don't know, that's clear, and they're going to be profound, because if they weren't, then it would be pretty easy to figure them out. And what is going to uncover those things? And evolution, I think, has been very convenient for that purpose, in sort of saying, actually, it's much more complex than a genetic algorithm.
Cool.
Yeah.
Can I actually jump in with a question for you here? So it's interesting to me that you said we don't really understand evolution well enough to simulate it. I always thought, and you thought about this so much more, I always thought about it as, well, one problem is obviously there's this massive parallelism, and it just would require a massive amount of compute to simulate. We may still understand the principles and the mechanisms, but we can't actually afford to compute it. And the second kind of bottleneck would be that, well, it depends so much on what environment you're doing the simulation in, and maybe conceptually we understand the principles again, but we don't have a good enough idea of how to design a realistic enough world to run it.
Yeah, so I don't think that so there's one point there about compute is true. There's certainly a big difference between compute in nature and the compute that we have available to us. But what's I think kind of really interesting is that I don't think that even if you were given that amount of compute, that we would know what to do. I think it's fair to say that you wouldn't want to come back 10,000 years from now with current genetic algorithms and be extremely excited to see what was there. Now, things might be just starting to change now because there has been progress like in the last 10 years or so. So maybe some argument like just today, like we're starting to think, well, maybe it would be worth coming back in 10,000 years, but I'm not even sure about that right now. And so I think if you really understand the state of evolutionary computation, then you would have some doubts, like even given a huge amount of computation, whether it's going to be like Earth. Then the question then is why? Well, part of it is what you said, I think, is like that the environment is a huge issue here. And that's part of why evolution, thinking about it algorithmically, is interesting, because it starts to tease out these issues where there are actually deeper questions. Like, why does the environment in our universe or our planet support what seems to be unbounded innovation over like billions of years? Like, that's incredible. What are the properties that account for that of this universe? I mean, it's almost a philosophical question, like what makes a general environment open-ended or support open-endedness? And we don't actually know. We actually don't know what the answer to that question is. Again, if we did know the answer to that question, we would use that to implement something. There's lots of speculation. I mean, in the artificial life literature, people talking about things like the richness. There's richness in the universe. But to me, that just begs the question, like, well, what exactly is richness? What does it actually mean? And like, what is the set of systems that have this property? Like, hopefully it's not just like the universe itself. I don't think that's true. I think if we did think that's true, we'd probably be stuck. But then we have to start thinking about what those properties are. And I think that's the healthy thing about thinking about evolution, is that it does force those questions on us. I don't think the environment is the only question, but it's one of the remaining big ones, I think, is how to design an environment that supports this kind of like unbounded continual innovation forever. And I don't think we've cracked that quite yet.
Well, yeah, I think that's exactly one of the main things also people in reinforcement learning just have to think more about, because so many of these environments, like, what interesting behavior are you expecting to come out of this anyway?
Yeah, absolutely. Yeah, this is not just about evolution, it's also about reinforcement learning. And I think there's, because of openness, they're kind of merging in some of the questions that confront them. And I don't like to pigeonhole myself just as an evolution person at this point, because the questions are just as salient in reinforcement learning. And maybe they're basically the same question, like things like that. Like, and I think this is really fascinating. Like, if you look at some of the coolest demonstrations of like sort of weekly open-ended behavior that have been achieved, which are real achievements, which are things like Xland or like the hide and seek work, or Poet or something like that. There's like a whole set of things, but they all are going to plateau. We know they're going to plateau. They can go for what we might consider a long time, but it's not a long time compared to billions of years. And so what is missing? Like, why is this? And why is this so hard? And why does it seem like contrivance like gets caught up in this so much? Like, we have to contrive so much to get anything like that off the ground. Like, we almost anticipate what all the discoveries are going to be before we even start the system, which is kind of like contrary to the whole point. Like, we don't want to have to anticipate what the discoveries are going to be. That's what makes it so rewarding to watch an open-ended system, is that it's supposed to be surprising. And yet when we design environments, we're almost anticipating all the things, like the agents are going to build shelters. Like, that's what's going to be cool about it. So we're going to give them blocks so they can do, but that's kind of disappointing. Like, we don't want to have to think of that in advance. And so this is a really interesting mystery, I think. And by the way, this is really cool also because it's outside the usual intuitions of machine learning. Like, if you think about all the things that we're good at thinking about in machine learning, like you think about things like following gradients, and being able to optimize very large deep structures, or whatever it is that the intuitions that we're developing over the last like 20 years or something like that, none of those have anything to do with environment design. Like, environment design is a whole other discipline, which is basically like completely virgin territory, because there's no experts on this. There's no study of this. There's no theory. Like, nobody knows anything about this. So it's extremely interesting for that reason, because like it's completely unplundered. All the low-hanging fruit is still there. It just it's a whole field that needs to be developed.
Yeah, maybe just to comment on this. I mean, I feel like we mentioned Xland, hide and seek, and these kind of environments, right, that we create and then we do our research in it. And I agree, like, mostly I think we are anticipating somewhat the kind of solutions that the agents would show, right, if they, learn the right things in the right order or whatnot. But I'm wondering, like, to what extent this is really problematic, right? Maybe we should like start with existing environments that we look into in terms of, okay, what are the kind of maybe still simplifying assumptions that are baked into those compared to, let's say, the real world. And then we see whether we can already use open-endedness to kick off a process that gets us to a solution within that environment. Right? I feel like right now we talked a lot about open-endedness in terms of this, this really kind of billion-year process that accumulates a lot of really exciting and interesting stuff. And that, to me, is super exciting. And I love to think about these things. And I, this is great. But I think at the same time we have a, I think, very dire need, right, to solve real-world problems with things like RL, where we see RL failing miserably, right? Just think about any kind of environment that has very sparse reward, where maybe it's partially observable, stochastic environment dynamics, procedurally generated or whatnot, right? I mean, RL is doing, at least vanilla RL is doing terribly right now, and we need, like, maybe we can already do enough or a lot with open-ended approaches towards solving such kind of more kind of short-term problems. And I think that's what I would love to see a bit more. And I would love to see, I think, us, and I fully agree with what Ken said, right? I would love us to become better at kind of assessing the environments that are in front of us, right? Whether we build them ourselves or whether we take existing, for example, games, we need to get really good at systematically investigating, okay, what makes this maybe a difficult or an easy environment. I think we've, for example, too long just went with Atari and thought that the things that we see there emerging in terms of AI agents is something great, but actually now I think we realize many of the behaviors there are due to just properties of the simulator.
Yeah, it's okay if I respond to that. That's an interesting point. That, I mean, I would acknowledge, I agree that like we don't just want to create like large open worlds, like it's kind of an A-life theme, and just see what happens in a billion years. That's not like a practical thing. That is still, I think, worth thinking about, because it's real. There's powerful implications in its own right for doing that. But also we want to solve problems today, like you said. And so it gets a little complicated how that, I think, intersects with open-endedness, because open-endedness has these principles of like there are certain things that you can only do by not trying to do them, or sort of like it's through the divergent process of finding all these stepping stones that it opens up all these things that you couldn't do before. But if you just tried to do one of them, like you weren't doing it through a divergent process that opened up all these stepping stones, you would get stuck and not be able to do it. So it sort of suggests counterintuitively that like some amount of open-ended process that isn't necessarily aimed directly at the problem that you're interested in will be necessary in order to solve the problem that you're interested in. So that kind of raises, so it maybe starts says, well, maybe there are preliminary environments where sort of open-ended type of development happens. Then those things could be transferred into specific environments because they're so sophisticated in certain ways. Or we can identify the ones that are the right stepping stones to put into the environment that you care about. And then our problems might get solved. So we're still back to thinking about sort of open-ended environments because it can generate those stepping stones. And we can consider maybe going into environments, specific environments that we want to solve, like real world problems, and trying to do something open-ended just in that environment. That might in some cases do something interesting, and in some cases it might be poorly thought out because maybe we need to be in other environments first because the stepping stones are circuitous that actually lead to where we want to go. And also there's a question of interestingness in some, like there are some environments that are fairly narrow, like say the game of Go, where still you could argue there could be an open-ended process inside of Go. In fact, you could argue that there has been like an AlphaGo or something like that. And so, but then, what is the limit of that? Like, is that still interesting if we let that keep going? Like, how long do we care? Like, a bit once we get to strategies that we don't even understand, and they're still just Go strategies, not strategies for any other purpose. And it gets I think hard to think about what that process is actually achieving. But we can certainly do things like that, and it might be interesting.
It's really hard to think about, like, what do we even mean by interestingness, right? So maybe one guiding direction there is, well, if the long-term vision is to build something that is intelligent in the way a human is intelligent, if we're just trying to discover some kind of principles that let us build a simplified version of a human brain, then we can ask the question, well, is this process going to bring us closer to that or not? And then I would argue the Go learning, even though it's pretty impressive, is probably not bringing us that much closer compared to tasks where there's more perception and maybe more interaction between many different agents and so on. I don't know if we should get back to the original question, though. This is really interesting.
Well, I think it's an important point to highlight, because that is a danger with open-endedness, is that it's not, while it's doing something interesting, it may not be moving you towards what you care about. And from the perspective of AI, that's a big problem. I mean, because we're basically saying, like, by assumption, by doing AI, we care about AI. So it's like, while this process may be doing all kinds of cool things, like getting good at Go or something, is it moving towards some general AGI kind of system? And maybe not. Openness doesn't guarantee anything like this. And I think that tension between like having a healthy open-ended process and being in control of where it's going is one of the central like puzzles of the field, because it's almost like a paradox. It's like the more I try to control where it's going, the less open-ended it is. But if I need open-endedness to get where I want to go, then I'm in a paradox. And somehow we have to grapple with that in order to make use of this, or to actually like direct it, which is, again, paradoxical to even say direct an open-ended system, but to get it to actually produce things that we want right now. And that's why I think, like, to some extent we need to be a little more open-minded in sort of the early days of just let it go, because we can't really get out of this paradox. We come from flatworms originally. Like, those are great grandmothers going way back as a flatworm. If you went back to that point in time where there were flatworms, you wouldn't necessarily want to be like checking for intelligence there to figure out which is the path we should go down to get to like human level intelligence. Like, you're not going to give IQ tests to flatworms or the other animals around during that period of time. It is completely obscure, like, why flatworms would lead. This has something to do with the emergence of bilateral symmetry or something like that. But this isn't the kind of thing you would understand looking forward. And this, I think, illustrates a problem for us, because like the equivalent of the flatworm that's going to lead to human level intelligence in AI is perhaps not very easy to identify. And so when do you make the switch? And will you actually prune out the flatworm before we even get there?
Maybe on that topic, I mean, I'm wondering to what extent we are thinking too much about open-endedness as a process that starts from scratch, right? I mean, we have human civilization right now. We have a lot of information content, going around the world. We have Wikipedia, all kinds of, human knowledge condensed in all kind of natural language and information and structured data and so on. So should we think about maybe open-ended processes that from the get-go start to interface with basically what's already here, right? They don't have to necessarily start from the flatworm, right? Start from scratch, or maybe they have to in order to even, for example, understand natural language at some point. I don't know, but I'd love to, I'd love to hear what you think about that.
I think that's a great point. Yeah, I think we don't have to start from scratch, and this is where deep learning starts to be really interesting. That it's like, let's skip a billion years or something like that. We should definitely do that. Like, let's not start with single-celled organisms if our goal is AI. We could start with single-celled organisms for other reasons. If some interesting things could happen that might be just interesting from an ecological perspective. But if we want to do AI, let's skip a billion years. Like, there's a little danger there that like we actually are not, we're not the right stepping stone. Like with everything that we've learned in deep learning, neural networks, and machine learning, everything like that, we maybe reinforcement learning, maybe it's all like wrong, and then we're screwed. Like, because like we're going to focus on the stepping stone for the next few decades, and we're actually going to hit a dead end. But assuming that these are all somehow like getting, plus like the existence of civilization right now, and the fact that we can interact with it, assuming that mix of stuff is actually allowing us to skip ahead, that is actually, I think, exciting and a good opportunity, and something that should be taken advantage of. And so, like, when we think about the flatworm, we're talking about something here that's much more like, an alien artifact, which is pseudo-intelligent. It doesn't look like anything analogous in nature, because it's like a current thing that's been trained on information from civilization that has way more intelligence than a flatworm, but isn't like any organism that ever existed on Earth, but might be in the large search space of all possible intelligence as a stepping stone that does lead to AGI. That thing is really interesting as a stepping stone that open-endedness could then build off of. But we still have the problem. Like, it's just that we're closer in the space to something like an AGI, but we still have the problem that we still might prune out our flatworms. Because like you might think, well, okay, so now we're so far advanced, let's just push it directly, explicitly towards high IQ or something like that. That might be the wrong thing to do, even though we're so far advanced. Because like, this is a very strange part of the search space. It's not analogous to anything we've seen before in nature, and it might be that we want to go through sort of orthogonal seeming puzzles and then wind back towards something human-like. And so we don't know that yet, so we still have to be open-minded. But I think we certainly benefit from accelerating forward.
I think it's also interesting to think about the open-ended process of the learning of one individual, where I think maybe there's a pretty close connection, symbiosis there between ideas about open-endedness and machine learning, because we want to build an agent that can learn about all kinds of new things and invent new ideas throughout its lifetime, and we don't want to just tell it, here's the reward, please, get really good at cleaning up the kitchen or get really good at playing chess or something. Mm-hmm. So I think that's like one aspect where open-endedness and AI definitely need to come together, and both need to be in place. And I guess to come back to the original question a bit, when we're focusing on that, I mentioned the adaptability earlier, and to adapt to something, you have to know about it. So you definitely have to absorb a lot of information from the world into your internal state in some way or another, right? If you only have 10 parameters in your brain, then there is just not that much information you can absorb, and so you can't adapt that well to a lot of different scenarios, right? So I guess that's the motivation for me to study world models, because that's how the agent can absorb all the knowledge, ideally, as much of the knowledge as possible. And that connects to the second point of not being bound to a task in a way that is fully agnostic to the task, and then you can do all kinds of things with it. And you can do unsupervised exploration objectives that are non-stationary. You can do empowerment objectives where the agent tries to have a measurable influence on its future inputs and so on.
Yeah. So I agree that in the open-endedness of individuals is also really interesting and should be part of the discussion. So it's a good thing that you brought that up there. It's not just about populations, and it does seem, I've believed always that it does seem like people are intrinsically open-ended. It's another reason that the field of AI needs to grapple with open-endedness, that we are not objectively driven like reinforcement learning algorithms. And like, I think that, you know, part of why we achieve what we achieve, even like really early in life, is because we implement open-ended processes to get there. We don't do it through like optimization towards an objective. And so something like learning to walk, I think, like it's not like over the course of early human development, like a baby is actually trying to figure out how to walk. Like, at least I don't believe that. This is totally speculative, but I think it's more that the baby keeps finding stepping stones in a divergent, open-ended way. Like it says, oh, I can move my arm around. Like that's kind of interesting. Where can we go from here? Like this is going to lead somewhere. This is much more to me like an open-ended process than like a convergent process, which is optimizing towards some point. It's just that some open-ended processes lead to inevitable ends. Like so, like each human is its own open-ended process, but inevitably we almost all come across walking on that road. And so I think that the concept of inevitability is an important concept that doesn't really come up much in discussions of openness, but it should, because when it comes to individuals, we're interested in inevitable things that happen through open-ended processes, which is much different than like setting a reinforcement learning target and just trying to optimize towards it. But in the bigger picture, I think this is that like in terms of individual open-endedness, we have to grapple with that as a field. And it's funny because like there's this, because of the way computers work, it's grayed or fuzzed up the distinction between individuals and populations and makes it confusing in some ways, because now you can sort of talk about like populations as in many physical entities going out and doing things, but then trying to merge them into one unified brain in some way. Or it could be like there's a single massive neural network behind all those things that are learning now simultaneously, and then that becomes this generalized system. And whether, you know, when do we benefit from thinking about things as discrete populations, like actually separate entities, versus like this giant hive brain where everything is sort of like coalesced into one thing? And that is also like a discussion, I think, like, can you get to where we want to go without an actual genuine population of discrete entities, like from some giant super entity?
Yeah. I'm also curious just to ask a follow-up question to one thing you said before, which is I'm really curious what you think about exploration objectives in reinforcement learning that are often non-stationary, but they are still an objective, and they do lead to kind of interesting behavior, but you know, when nowhere near where we would like to go with that, and you know, maybe that's a totally different, maybe it's a totally wrong approach from your perspective.
Yeah, I think they're on the right track, but I think it maybe what they are is more like the easy part of the problem is one way to think about it. Like they're very similar to novelty search, which is the algorithm that I worked on with Joel Amen, which was in evolution, like this idea of like just trying to evolve towards novel behavior as opposed to towards some specific type of objective. And so that's like an exploration objective for evolution. And then the reinforcement algorithms are very analogous in some way. But they are kind of just saying, given a space of possibilities, let's create an incentive system to move through the space to the most interesting points in that space. And that's kind of hard, actually. So I don't know if it's like fully satisfyingly solved, because like the incentive system itself can be complicated. Because it's like, what is actually novel? Where do I actually want to point you? You know, what does it mean to discover something new? Like the question is not completely resolved in either field. But even if you do resolve that to some degree, to some satisfying degree, there's this other dangling thing, which is, where do the new opportunities to do new things come from? So that goes back to this environment problem in some sense. Like I think a real open-ended system requires two sides of a coin. Like one is like this incentive to explore, and that I think we're getting a better handle on. That's getting pretty good, I think, in a number of fields. But then on the other side is like the constant emergence of new things to do, so that the exploration can continue. And that doesn't necessarily happen. So it's like you can create like a quadruped robot and explore all the different ways it can move. And we've gotten pretty good at stuff like that. And I think that's satisfying. Like then it starts to walk and maybe starts to run and hop and do all kinds of things all in one run. That's really cool. It's kind of weakly open-ended, but what happens when you run out of those things? It's not going to start writing poetry. And so something's still missing if you want that to go all the way, like whatever that would be. That's just like a demonstration that the exploration objective is working. But the problem is, like even there, like that's a narrow domain, so it's easy to set up the exploration type of incentives. I shouldn't call it objective, the incentives for exploration. because like it's easy to sort of parameterize like what different kinds of gates are or something like that. But poetry isn't anywhere in that parameterization space. Like, so you're never going to even capture it, even if it did start happening. Like, let's say that robot does start writing poetry, like we're not going to see it, we're not going to notice it. How would we set up a kind of a diversity representation which would actually be able to notice something like that in the first place, or an environment that would support it and appreciate it? So I think it's a step in the right direction, but it's the easy step.
I think, I mean, just to chime in, I think we do have environments, simulation environments right now, right, that obviously are limited, so they only allow us to, I guess, test how far a weak, I guess, open-ended approach will get. But like if you take, for example, Minecraft, and then you just craft, right, a grid world version of 2D grid world version of that. We have NetHack, procedurally generated, very complex, rich environment. And in these environments, I think there's so much room, right? We should, if indeed like the first side of the coin was solved, right, we still should see a open-ended or weakly open-ended novelty searching agent already see like exhausting, I guess, the possibilities within these kind of confined simulated grid worlds. But we're not there yet, right? I mean, we still have tons of research to do in order to even get that off the ground.
That's
it's
fair.
a matter of scaling, though. I think we can, like, the current concepts will probably work in these environments. It just takes a lot of compute to optimize them, and yeah, we need to make our networks bigger, and we have to train them for a lot longer, and we have to put more agents into those environments. And I think that will probably get us to the point where the next bottleneck again becomes the complexity of the environment.
Well, I think before that we already have one tough nut to crack, which is, if you just take your craft environment, for example, right, it's procedurally generated. So how do we measure novelty, right? You can't just, I guess, count the states that the agent has observed, because that's already like a pretty big state. I guess you could maybe, but
we actually built that in. The idea of having like 20 tasks that semantically meaningful, at least to a human, in that environment. And so when you run the agent, you will get, you can count how often it has achieved each of the tasks. Either if the agent tries to, it gets a reward, or even if it's fully unsupervised and it's just trying to follow its curiosity. But you can get a bit of like a spectrum of the interesting things that it has discovered that way. And I think that's the first step, but I think we should go much further in that direction and beyond the crafter environment. And we should have benchmarks where there's a lot of things the agent can do in the environment, and a lot of different things too. Maybe we want to have 5 tasks that we can measure because it's a simulator that specifically require long-term memory, and 5 tasks that specifically require like out-of-distribution generalization, those things. And I think we would, that would unlock a new efficiency or progress for reinforcement learning.
So you want to build in some prescripted tasks, basically, that are just more diverse in some sense, and like it's implicit in, say, Minecraft. Is that sort of the idea?
I think we want to measure a lot of different tasks in the same environment. It's kind of pointless to train an agent on 55 Atari games that are, first of all pretty similar, and they are not sharing any parameters in any of their knowledge. We're just developing 55 narrow agents that way. Having one environment where you have 50 tasks is a lot better. Now you can afford to make the agent better. You're not wasting your compute as badly. And then the question is, do we even have to tell the agent about all these tasks, or can we just say maybe we can solve this problem without any task rewards through like a purely unsupervised approach? But we still have these tasks and these task rewards for us to look at as proxy metrics to get an idea of whether the thing is discovering interesting things.
Yeah, I mean, go ahead.
No, I just wanted to comment. I think that exists, right? I mean, we have, as I mentioned, we have NetHack, and I want to like boast too much about it, but it is a very complex, rich environment with like, I think 75 different actions and hundreds of different entities and monsters that you have to learn how to interact with. And there's lots of kind of waypoints, right, that you should like pass by on a episode towards winning the game. So that is, to me, I mean, it's definitely not the end of the story, right? It has lots of limiting assumptions in there as well. It's a symbolic grid world, but it is covering, I think, the properties that you mentioned. So I think that's there, right, for us to start exploring and do research on. And I think we've only scratched really the surface of the challenges there, as you mentioned as well. I mean, there's so much more that needs to be done in order to have, even just within the confines of that kind of procedurally generated simulated environment, a process that can really exhaustively find all the different ways of reaching, for example, a certain part in that game.
Yeah, so I just wanted to comment because I think we should endorse that kind of, I guess you could call it environment engineering. I mean, if you create environments that have like this broad diversity of possible tasks, like that's definitely helpful for open-ended research. But I'd also, just keep in mind that like what really becomes a mystery is like where do new cat tasks come from, beyond the ones that we imagined before we implemented the environment. And that remains a frustrating challenge, I think. Like, that's what we really want in the long run, is to not have to think about all of this a priori and just be able to have it emerge from the environment itself. Obviously, there's a little danger there, because if it emerges from the environment, we may not care about the tasks. But that's kind of the whole problem. Like, we want the environment to generate tasks that we do care about. And like, with respect to something that's ill-defined, like why do we care about any of these tasks at all? I guess because we think they might lead to AI. Like, ultimately, it's not like we really care about like somebody in Minecraft, like, I don't know, getting a particular ore or something like that. It's like we care about AI. So we think like this is a kind of a milestone on that road. Like, it's at least helping us conceptually. That's probably true. But that makes it even fuzzier, like whether I should be or shouldn't be interested in something that emerges in a more organic way from the environment. So we just have to figure out, we have to confront this challenge eventually, is where will the tasks emerge from the environment? It's true that also we have the current universe at our disposal. We should also remember that. I mean, the current state of Earth and the data that exists, which also can enter into that.
Yeah, I'm imagining that we, like, right now there's so many kind of obvious tasks that in AI is supposed to solve, but it can't solve yet. And you can define them in the environment, and that's only the first step, because ideally, if you're designing an agent that can solve them, especially without the reward, I imagine that if you run it for longer, it will start to discover interesting things. And then I guess by definition, if we didn't think of these tasks, it'll be very hard for us to measure them, but we can still look at the video and see what it does and be surprised, hopefully. And maybe we're surprised in a negative way. It's like, oh, it found this weird quirk here. And then there's the iteration loop. And then that means, okay, now we're learning something new about the environment design, how we have to change the environment, or the agent objective or agent mechanism to then get rid of this of this kind of like degenerate solution and run it again, and then there will be another degenerate solution. But over time, I think we'll get more and more interesting, like also unexpected behaviors out of it.
Mm-hmm.
Right. I mean, I think we should also maybe think more, I mean, less about basically designing specific environments and do, I think, more of what I guess Poet is an instance of, which is like learning to create the environments while we learn to solve tasks within these environments. And I think we only, as a field, scratch the surface on that direction, right? I mean, then you think about, okay, just design spaces basically, right? What are the kind of components that, let's say, some agent can put into the environment for then a student agent to get an interesting task to solve, that could get us away at least a little bit from like these kind of handcrafted, even when they're procedurally generated, but handcrafted kind of environments that we use for research right now.
Yeah, definitely. I mean, it is interesting to think about how nature did this. So it's like in nature, the way that this worked out was that the solutions were also the problems. That's why you can keep generating more problems. It's like trees are a solution in some sense to like survival and reproduction. So you get the tree, but then the tree is now a new problem. Like, how do I get a leaf? Well, I mean, if I want to eat it, like a giraffe. So like the giraffe is now a solution to that problem. And now it's also, somebody else could also be a predator of a giraffe and so forth. And so like we are all, it's not just even just like a sort of predator-prey relationships, but we're all actually opportunities for each other in many ways, not just in terms of killing each other. But like, just like this conversation is because some of us are creating opportunities in different ways for each other and creating new problems as we try to confront the ideas that we're presenting each other with. And so somehow it's like internally generated by the agents themselves, but the agents are both the solutions and the problems, and generating the solutions and the problems. But it's so complex that it almost seems like too much to try to do all at once. Like for us, I mean, it's a real practical problem. How do I set up a world like that and actually get progress towards AI? And yet somehow it's also intriguing. Like that seems like extremely powerful. I mean, look what it did. So you can't discount it either. But I guess where it points is towards multi-agent. Like that, at some level, maybe you need that kind of multi-agent aspect to really keep a process like this going for a long time.
Yeah, and this connects to having multiple tasks, because the benefit of, like, maybe if we build this like fairly realistic, very complex world that allows for a lot of emergent things to happen, maybe that's a bit out of reach right now for current methods. But on the other hand, if we define enough tasks, there will be some very easy tasks and there will be a lot of very difficult tasks. But we could, in principle, already start doing research on these environments. And our agents will, they'll maybe in Minecraft start to like collect some wood and that'll be it. But then if we define enough proxy metrics there, then I think those environments can guide research for a really long time. And they can give you an interest, like a useful feedback signal to the agent or to the researcher as well, of where we are along the spectrum of the things that can be done.
Yeah, and I mean sometimes like breakdowns or hitting a plateau is actually useful, because it does expose like a deeper issue with like, why is there a limit there? Like what is preventing things from moving forward? And sometimes we need to be confronted with that explicitly. To make progress, we need to actually understand what the questions are that we should be asking. So even if you know that like this can't possibly be like Earth, like there's no way it's going to go that far, it's still, because of where we are today, I think you can expose things that are still really instructive, that can help us make progress.
Okay. Tim, would you like to answer like the original question on?
All right. So the original question is why I'm so excited about auto-curriculum learning, if I remember
Yeah,
correctly.
pretty much that. Yeah.
I mean, first of all, just want to agree with Max and Ken. I mean, at the end of the day, I'm not like married to a specific tool in the toolbox. I think it's about, kicking off interesting processes that can accumulate interesting behaviors and lead to agents that can generalize well to like novel situations. We just found in our lab, auto-curriculum learning to be a very tangible, exciting direction that we spend quite a bit of resources on. So that also links to what Daniel just said. Like, imagine you have a relatively complex environment and you can sample, let's say, problems within that environment space, right? And now you have a distribution of some of these instances are super easy, like your goal is just next to you and you just have to move right and you're there and the agent is happy. And then some of them are extremely complex, where the reward only appears after, let's say, hundreds of steps and you have to do all kinds of really complex behavior. So one of the things that we were quite interested in is how can we kind of sort basically that kind of space of tasks, right, in a way that maximizes learning potential for an agent. And so we've worked a lot on that and found ways to do this, I think, relatively well. It's called prioritized level replay. And the interesting bit is that we then found that we can even use that for what's called unsupervised environment design. So if you have a generator that just keeps on generating lots and lots of problem instances, you can keep around in a buffer basically those that are for a specific agent at a specific time step, useful to revisit and learn from. Again, this has obviously connections to Poet and other approaches that are in that space. But I think like this kind of idea of figuring out what are specific problems that an agent should tackle at a specific time of in their life, right? That is something that's very dear to us, and I think specifically when that's combined with a way to design automatically, have another basically parameterized agent that learns to design these problems for the other agent.
Yeah, something like what you see in Poet and Paired, and okay, so now for the audience questions. Is it okay if we continue a little bit more because we're past the 1 hour?
I'm okay. We can do it. I'm having fun. So.
Okay. So the first question is something that you talked about is Is there any work in environment design to look at now?
That's a good question. Well, I mean, one way to answer it could be just, well, I mean, look at any experiment with the word open-endedness. Somebody had to design the environment, so there's basically an environment design implicitly in all of this stuff. I mean, like Xland is, there's thought behind that environment, and so you can see the thinking behind that. But I think, like, in the spirit of the way I talked about it, I would say basically no, because like those environments. But I don't mean to criticize specifically one thing. I mean, I'm basically saying everything is like this, like including things I've done. Like usually you see environment design in the sense you see that like somebody created an environment with the intent of having a somewhat weak open-ended process inside that environment. And they could explain why. Like it's like, well, these are the reasons we made the environment this way. And some of those reasons are interesting. But what I think you don't necessarily see is grappling with like the deeper, almost philosophical question of like what actually makes an environment support really, really long-term open-endedness. I don't know of anything that like in like academic literature or scientific literature like actually grapples with that question. And so I think it's like it's a totally new thing, and it's hard to get started because you're probably not going to publish something where you just talk about it. So like to really do something there, it's risky. Because it may not look a lot like progress at first, like to start grappling with pseudo philosophical questions. But I do think that we have to grapple with that at some point, like to really make progress.
Yeah. Well, I think more short term. I mean, there's work like Yours said, like mentioned paired, right? I mean that and poet as well. I mean this, we discussed this a lot, right? But I think it's an interesting stepping stone along the way of potentially designing very complex and rich and interesting environments. Paired has been now extended, multiple times towards being able to generate quite complex curricula of environments that then allow agents to train generalizable behaviors. Is something that we've done a lot over the last year. So I think I would start looking there, basically, not like handcrafting, designing environments, but kicking off processes that over time create interesting, complex environments.
Yeah, I guess one requirement, or maybe not requirement, but one step that's slightly easier than the question of what facilitates open-endedness in environment is how can we even categorize the space of possible environments in a formal way. And there's very little work on this, but there is a bit of work. I remember a DeepMind paper from maybe a year ago where they try to infer some kind of underlying graph for the environment, and it seems to work for pretty simple environments and for very complex ones as well. A lot of the things they looked at in the paper were games, so it goes from like tic-tac-toe to like a full Go board and some environments with pixel inputs as well, and you get some kind of similarity or distance measure. I think it's a very early step, but I would like to see more work in the direction of categorizing what are even the fundamental properties of environments that we should be thinking about. Like, what is the set of these, things that might be interesting, and how can we formalize them, and then we can connect them to what behaviors they maybe not lead to, but at least enable in the environment.
Okay,
That's
you can go ahead.
no, that sounds like a good idea. To start to like sort of formalize environment properties, or just try to think about them in some systematic way, at least to get that kind of component of this field going a little more formally, I guess, because it's sort of just under the hood, like it happens, and a lot of interesting thought is there already, but at least it's not really explicitly thought of as like a field in its own right.
Okay, and now we have a couple questions that are like combined then, hopefully. So what's the application of open-endedness? Is it something very like geared towards making strong AI or general AI, or is there some other way of using those general agents to produce like real world applications?
Who should go? Or I can.
Oh, okay.
I can take it.
Let's go alphabetically. So, Denjar.
Okay. what are the applications of open-endedness? Well, to me, I would like to build a system that can learn within a single lifetime very interesting, like a lot of different diverse things, and adapt to different situations like a human brain does. So that's the direction or vision I'm working towards. And there's, for one, just understanding ourselves better. That may not be something you can make money with immediately, but there's obviously lots of applications where you could replace work that requires humans to do it right now, and you could start automating things. For example, maybe eventually, very long term, some implications for psychology and diseases and so on. But an assistant that helps you, to really understand the world. Like we have these AI assistants in our phones now, and they are kind of useful for, I guess, for like querying some fixed knowledge base. Like they can fetch things from Wikipedia and so on. But I mean, that's obviously still a very early version of what could potentially be done with a system that actually understands the world and and understands it in a way more similar to how we understand it. And I think that requires some degree of open-endedness as well.
Chen?
Okay, yeah. So what can open-endedness give us in the real world? I think there are several answers to that. One is just AI. I mean, if it is true that you really can't get to AI just through a more conventional type of optimization process, I mean, just need it. So that's what it's going. If anything's going to deliver AI, that's part of what's going to deliver it. But at a less grandiose scale, perhaps you also have to consider that sort of sub goals of artificial intelligence, or just intelligent agents that are not like human level, but that do things that are useful for us. Some of those also will require open-ended processes to obtain. So there's all kinds of things that we might want that aren't like insanely ambitious, but still might require an open-ended process to get. So those are other things that open-endedness can deliver. Now, on top of that, you have to consider that open-endedness is the power of creation. Like if you really think about what it's about creativity ultimately. And what is the most prolific, most creative force that's ever existed in the universe? It'd probably be natural evolution. It's insanely creative. It created all of living nature, and civilization as well. If you look at it in terms of all of art and all of science, and all of the things that humans have invented, it's all an open-ended process. So creativity is at the heart of open-endedness. And so it can start to deliver creative products that right now only humans can deliver. Some of them can be extremely exotic things that we've never imagined before. Some of them can be addressing needs that we actually have and that we've identified. Some of them could be for fun, like clothing and jewelry and things like that, art. And at the same time, because many of those things are things that we humans care about, open-endedness can be a partner to us as humans. And I think that's one thing we haven't touched on much, is open-endedness with humans in the loop. But likely that's going to be a big thing because we want open-endedness to do things that we actually care about. And it's really natural because we are just inherently open-ended. We're inherently creative. We talked a bit about this. Individuals are open-ended over their lifetime. Society over history is open-ended. And so we naturally would interact with open-ended entities. Like they raise possibilities to us, we build on those, and we send them back to them. They raise more to us. That's a very natural divergent process, and the AI can start to participate in it if it is also inherently open-ended. And by doing that, I think it amplifies our creative abilities because a lot of us as humans can't participate in a lot of aspects of the exchange of creative consumable ideas right now, so like music or something like that. But in the future, theoretically, I mean, if open-endedness really breaks things open, we start to become participants because we don't have to have all the skills because the computer can fill in the gaps. And so we can start to participate in things where otherwise we wouldn't be able to in a meaningful way. So not just humming in your bedroom, but literally creating things that are like radio quality. But because you're part of a process where you're participating but not doing everything. So I think open-endedness has a huge spectrum of things that it can deliver, considering that it's really a deeply fundamental in sort of what it means to be human, and it shouldn't be underestimated.
And Chin?
Right. I mean, I don't think I have much to add to that, other than I think we should separate maybe, I guess, this goal from kicking off this process that eventually might lead to AI or AGI from more short-term applications that will already be really amazing, right? I think we'll see much more ideas from open-endedness to be used to be, like, for example, train agents that can generalize better, or like lots of the applications that Ken also mentioned. And I think it's fine to have both around, right? It's fine to say, look, to some extent, that's the big vision. This is where we want to, eventually, go to in the next decades or so. But here's already things that we can learn from thinking about it in certain ways, right? That we can build in kind of current machine learning models, current ideas for real world problems. I think that's a very healthy, I think, setup, and that's, I mean, I see myself definitely more in the latter.
Okay, and now for our final question, which we kind of got from Sarah Hooker. What do you think are like underrated papers in this field, in the field of open-endedness? So papers that came out, you said, "Whoa, that's pretty neat, that's pretty cool," but they didn't get the deserved attention. So let's start with Tim and then go the opposite order.
Yeah, I mean, I think one of the papers that definitely was quite influential for us was this paired paper. I mean, Poet was fantastic as well. I love that, and I think I got the attention it deserved. That's great. But I like really this approach of saying, look, you have an agent in an environment that learns, but you have also really control over what you put into that environment. You can like learn what kind of blocks or what kind of entities or objects to place where to create a really complex or increasingly complex problem for a student agent to learn. And so really that kind of paired paper has spurred a lot of kind of follow-up work in my lab, and that's really one paper I think that should deserve a bit more attention.
Ken?
I guess I'll point to like a whole literature, which is basically the artificial life literature. And I think it's really interesting how there's an entire stream of thinking there about open-endedness, which goes back decades, which is completely disconnected from when people talk about open-endedness and machine learning. And like to some extent that may reflect that there are different goals there. Those communities don't really have the same goals, and they're using the same terminology, but that's not entirely true. I think that there's certainly overlap, and I think it's always interesting to have cross-pollination from like very different places. And so I think I would encourage people to check out that literature coming from machine learning, and see what was discussed in artificial life and what was attempted there, and see how does that connect to what's going on today.
Yeah, I don't have a particular paper to point to. I think in general, we should, to be creative and open-ended, that means doing a lot of things and knowing a lot of things. So I think world models over reinforcement learning or model-free reinforcement learning is the right direction to go. And I hope there's already a good amount of upcoming work there, but I think it'd be nice to see more focus on that, especially combined with unsupervised objectives, like unsupervised exploration objectives that are open-ended in that sense, that they try to keep discovering new things, and not just like even if you care about plain task performance on something. The more complex the task, the more you will need open-endedness and unsupervised learning, and to even get there in the first place. So I think that's something we can all, I think the whole AI community can work towards.
Okay, so thank you all very much for coming. It was a great discussion. It was really, I don't know, funny, poetic that it's a panel about open-endedness, and suddenly you were asking questions to each other and not just like following the main questions you had. And yeah, I guess that's it.
Thank you. Thanks for having us.
Yeah, thanks for the invitation.
Yeah, thanks for organizing. It was a fun chat, and glad to get to know all of you a bit more. And cool.
Yeah, agreed. Good to meet everybody.
Yeah.